All right, let's go ahead and talk about Lewis structures and how we can draw the structure of different molecules. And so let's go ahead and get started with these notes. So Lewis structures, therefore, they are used to model what atoms look like in a compound, and they show kind of how the atoms are all bonded together. And this contains atoms that are covalently bonded. So they're atoms that are covalently bonded. And when we are drawing these structures, I'm going to go ahead and draw a Lewis structure down here. And so I'm going to do water. This here is a Lewis structure. And when we draw an element's symbol, essentially what that represents is the atom's core, all right? And the core is the nucleus in the inner electrons. And so what we're doing here is with these dashes and these lone pairs, what we're doing is we're showing the valence electrons and how the valence electrons are bonded, or how the different atoms' valence electrons are bonded with each other. So so again, the element's symbol is the core. Now, valence electrons, okay, so valence electrons are then represented using either dot pairs or dashes. And if the valence electrons are not involved in the bonding, for example, this one right here, these are lone pairs, we'll talk about those later. If they're not involved in the bonding, then they are represented using a dot pair. So again, if they're not involved in bonding, they're represented using dot pairs. Now, if the valence electrons are involved in bonding, then they are represented by using a dash. Okay, so if they're involved in bonding, they're represented using a dash, and here is a dash. Now, something to keep in mind is every single dash is a bond, and a bond requires 2 electrons, and so each one of these dashes represents 2 electrons. And so I want you to think about this for a moment. In this entire structure, how many electrons are represented in this entire structure? And the answer is 8. There's 8 electrons there. We've got 2, 4, and then 6 and 8. So now what I'm going to do is I'm going to show you the sort of rules for drawing Lewis structures, and I will go through them as we go, but this is what I'm going to start off with, and I'm going to start off with this here. What I'll say is, if you think about the Lewis, the valence Lewis dot structure for an element, let's think about fluorine, for example. Notice how many single electrons there are. So fluorine has 1 single electron. What I will say is, for every single electron there is, that will be 1 bond that element makes. And so fluorine, if you take a look, has 1 single electron, so it will make 1 bond. So this will make 1 bond. And I'm going to go ahead and off to the side here put number of bonds. Now, if you take a look, oxygen has 2 single electrons, so it will make 2 bonds. And we can see that if you take a look here. So look at that, it's making 2 bonds. It's making 1 bond with hydrogen and 1 bond with another hydrogen for a total of 2 bonds. Now, nitrogen, if you take a look, has 3 single electrons, so that'll make 3 bonds. This has 4 electrons, so it will make 4 bonds. And then I'm going to stop right here. This makes 3 bonds, and I'll include beryllium here. This makes 2 covalent bonds. And so these are the number of covalent bonds that those particular elements make. Now notice this makes 0 because it's a noble gas. It doesn't have any, it's got a full octet, and so it doesn't tend to make bonds. Now, the other thing we want to keep in mind is we want to keep in mind how many lone pairs there are. And so notice, I'm going to go ahead and circle the lone pairs. Let's circle them blue. And so here's 1 lone pair that nitrogen has. Oxygen has 2 lone pairs. Fluorine has 3 lone pairs. And then obviously the noble gases have 4 lone pairs. And carbon has 0 lone pairs and boron has 0. That's actually going to be really important to note that those have 0 lone pairs, all right? And that'll be relevant later. But the thing here is we want to keep in mind how many bonds does an element make. So nitrogen makes 3 bonds, for example, and then how many lone pairs does the element have? Now, I'm going to go ahead and talk about number 1 now. So when we're, let's go ahead and we're going to do this particular one here. And the first thing we want to do is determine what the central atom is. And there's a couple ways of knowing that, all right? So if you take a look at number 1, it says build the skeletal structure by choosing a central atom and then surrounding it equally by the other atoms. And so usually the element with the lowest electronegativity will typically be the central atom. Hydrogen, however, will always be a terminal atom, which means that it's going to be bonded to the central atom. But the way I look at it is when we're looking at this, the central atom is typically going to be the one that you have the fewest number of. And so what do you have the fewest number of? Well, carbon. Another way of thinking about it is typically going to be the one that makes the most bonds. Well, which one of these makes the most bonds? Well, carbon makes 4 bonds. And I want to actually add one more thing. I forgot to add one more thing. Let's add hydrogen here. Hydrogen has 1 valence electron. And so how many bonds will that make? It'll make 1 bond. So we want to keep in mind that hydrogen will make 1 bond. All right. So carbon is the central atom. So the first thing we want to do is we want to put the central atom in the middle there. And then we want to evenly spread out all of the other atoms. So there's 4 hydrogens here. And so the way we evenly spread them out is not like this. So we don't do this. This is not okay. Because can you make them even more spread out? Can you make it more organized? Yes, you can. The way you do that is by doing it like this. So now they all have equal amount of distance between each other. So you kind of want to make them equal amount of distance. Okay, so the next thing you want to do is you want to think how many bonds does each element make? Well, hydrogen makes 1 bond. Carbon makes 4 bonds. And the way we know that again is, look, carbon makes 4 bonds, and then hydrogen makes 1 bond because it has only 1 single electron. And so carbon makes 4 bonds, hydrogen makes 1, and so what you're going to do is you're going to start adding bonds. Okay, so hydrogen makes 1. So each hydrogen is going to make 1 bond with the carbon. Now carbon makes 4 bonds. And how many bonds are there on the carbon now? Well, there's 4. Look how that worked out perfectly. Now the next thing we want to do is we want to add lone pairs. And so if you take a look at carbon here, carbon does not have any lone pairs. So we don't add lone pairs. So we can leave it like that. And this is it. That's our structure there. So step 1, you put the central atom in the middle there. Step 2, surround the atom with hydrogen, or with the terminal atom. So this is called a terminal atom because it's bonded to the central atom. And then make them have the appropriate number of bonds. Okay, so let's go ahead, take a look here. So what is the central atom here? Well, the central atom is oxygen because again, it's the fewest number of them and it makes the most bonds. So oxygen's in the middle. And what I'm going to say is to evenly spread these out, you need to go like this. But we will learn that this is not the shape it makes, but that's okay for now. It's okay if we write it like this for now. Anyways, so now what we want to do is each hydrogen makes 1 bond, and if we take a look over here, oxygen makes 2 bonds. So notice how if we make this hydrogen have a bond with oxygen, and then this one have a bond with the oxygen as well, notice how oxygen now has 2 bonds. But we're not finished yet. This is a very important part. We have to add the lone pairs. And the lone pairs are going to be very important for next lesson. And so if you take a look, oxygen has 2 lone pairs. And so we go like this. And there it is. Now, again, each bond has how many electrons? How many electrons are right there? There's 2 electrons. And so notice how there's 2, 4, 6, 8. Notice how there's 2, 4, 6, 8. And so notice how we're satisfying the octet rule by doing this. All right, let's go ahead and go to the next one. Carbon, central atom. There's the fewest numbers, there's only one of them, so it goes in the middle. It also makes the most bonds. The one that makes the most bonds typically goes in the middle. And then we put the oxygens around. Now, this one's gonna be a different situation here. Let's think about this for a moment. So carbon makes 4 bonds. The way we know that is if we look here, carbon has 4 single electrons, makes 4 bonds. Oxygen makes 2 bonds. So how do we make carbon have 4 bonds and oxygen have 2 bonds? Well, the way we do that is there's not just a single bond here, but a double bond. You might ask, well, how do you know to do this? Well, what other way will that work? What other way will it work that you'll have 4 bonds in carbon and 2 bonds in oxygen? Because when you do this, notice how carbon has 4 bonds, and then each oxygen has 2 bonds. So you kind of it's kind of like problem solving to figure that one out. All right, but we're not done yet, because again, very important, we have to add the lone pairs. Carbon does not have lone pairs, but each oxygen has 2. And we want to kind of orient the lone pairs to where they're spread out as well. So the way you do that is you'd kind of put it off to the side here. And if you would imagine like this being an angle, this would be 120 degrees, this angle would be also 120, and then the angle here would be 120 as well. And the reason why that is because electrons repel each other, and so they don't want to be close to each other, and there's electrons here as well that are repelling. And so we just want to make it to where the electrons are as far apart as possible. And that is our structure there. Now what I want to say is this next one, I'm going to cross this one out. There's too much going on with it. You won't need to really know how to do it. It's a little bit more complicated, and there's some things about it that we don't really need to necessarily learn. So, but what I'm going to do is I'm going to go to this next one, and this next one has an exception with it. All right, so there's a couple things. There's 2 things that I'm going to really highlight with this one, and so this one I really want you to pay attention to. So the first 3 that we did, those are really straightforward. So those ones should be ones that they make the correct number of bonds, then you have the correct, and there's no nothing that's not normal. So this one's different though. So let's go ahead and talk about this. So nitrogen's in the middle, obviously, because it's the fewest number, and then we have a hydrogen, and we have a total of 4 hydrogens. Now, I'm gonna pause here for a moment. How many bonds would nitrogen be making if each hydrogen were to bond with the nitrogen? If each hydrogen were to bond with the nitrogen, it would make a total of 4 bonds. And watch, 4 bonds, right? However, what's the problem with that? Well, the problem is how many bonds does nitrogen typically make? Nitrogen only makes 3 bonds. And so in this situation, notice how it's making more than 3 bonds. And so this is what you need to do. If something gives you a formula where it is telling you that there is 4 hydrogens, that means there's definitely 4 hydrogens. And so we can make our 3 bonds here. And then what we do is, if you take a look right here, so number 3 says add bonds between atoms to satisfy the octet rule for each atom. Each bond represents 2 electrons. Now look at A here. If the central atom is satisfied, look at that, it's satisfied and there's no bond here. If the central atom is satisfied and there is a terminal atom that is not yet bonded to it, then force the bond between it. And what I mean is you just need to accept that this is making an extra bond here. And so if it gives you something like that, then what you need to do is you just need to add the bond. You just need to add the bond. Now, there is a reason why it's able to make this bond. We will talk about that later, but for now I just want you to accept that it makes that bond. All right, so let's also keep in mind that we had to force that bond. Now let's look at nitrogen here. Nitrogen does have 1 lone pair, so we want to add the lone pair. All right, but we're not done. We're not done. If you have something that's outside of the norm. Like this is normal, all right? So this is normal, this is normal. It made the appropriate number of bonds. But so this one here is not making the appropriate number of bonds. And so what we need to do is, if you're ever in a situation where you had to either force bonds or the structure has too many or too little bonds, like in this situation, nitrogen has 4 bonds instead of 3, what you then need to do is you need to verify the number of electrons. And so to do that, you need to count 2 electrons twice. You first need to count the electrons that are in the Lewis structure here. I'm sorry, that's in the formula. And then what you need to do is you need to count the electrons that are in the structure. So you're going to add up the valence electrons in the formula, and then you're going to see how many electrons there are in your structure. So let's go ahead and do that. So nitrogen has 5 valence electrons. Hydrogen has 1 valence electron, except there's 4 hydrogens, and so that adds up to 9. However, that we don't actually have 9 because somehow it became positively charged. And so let's go ahead and take a look at this. So for positive cations, what you want to do is subtract the number of electrons required to achieve the charge. And so in this situation, how did it become a 1 positive? It became a 1 positive by losing a negative electron. And so what you'll need to do is subtract an electron. And when you do that, you end up with 8 valence electrons. And so what that means is that this here has 8 valence electrons. And so this needs to have 8 valence electrons as well. So let's go ahead and take a look. We have 2, 4, 6, 8, 10. There's 10 valence electrons. And if you take a look here, if there are too many electrons, then what you need to do is subtract lone pairs from the central atom. So if there's too many electrons, you subtract lone pairs from the central atom. So we want to subtract these lone pairs. And there it is. And so now we got our 8. So we verified, we subtract our lone pairs. The last thing we want to do is put this in a bracket here. So put that in a bracket, and then we will make this a 1 positive. All right. The next thing that we're going to do is this next one here. And I actually just want to come back to this real quick. So again, if it's a polyatomic ion, you have to put it in a bracket and put the charge on the outside. All right, let's do this next one. So we have oxygen, we have hydrogen. Hydrogen makes 1 bond, and there it is. Now oxygen does have 2 lone pairs as well, but what's the problem with this? Well, the problem with this is that oxygen typically makes 2 bonds, and in this situation it's only making 1, and so this is going to be another situation where we have to verify the electron. So this is something that's outside of the norm. All right, so oxygen, there's 6 oxygens. There's there's 6 valence electrons. For oxygen, 1 valence electron. For hydrogen, this equals 7. However, how did it become a negative charge? By gaining an electron. So again, it became negatively charged because it gained a negative electron, and this is 8. And notice how there's 2, 4, 6 valence electrons. So what we need to do in this situation is add a lone pair on oxygen, and there it is. And then what we do, again, because it's a polyatomic ion, we have to put it in brackets, and then we put a negative there. And that's it. All right, let's go ahead and talk about this one. This one is a little bit of an extension of the other ones here. And so if we have this multi-carbon formula here, this has multiple central atoms, and you will learn more about this in AP Chem and in organic chemistry that you'll take in college. Goes a lot more into depth with this. So, but essentially, there's each carbon is going to be a central atom. And so what you're going to do is you're going to put a carbon in a row here, and then we have the oxygen here as well. Now, what you're going to then do is after each carbon, notice how it tells you a certain number of hydrogens or oxygens or something. Well, what the first one says is that there's 3 hydrogens. This second carbon has 2 hydrogens. So what we're going to do is we're going to put the hydrogens around that. And then this next one has 2. Now, notice how after the oxygen is a hydrogen, and what that's saying is that there is a hydrogen that is attached to the oxygen. And so essentially, when you're looking at this, you are just you're setting up the central atoms, right? So here's the central atoms, and then you're surrounding it with the appropriate number of each element that is saying that it's bonded to. And so again, each hydrogen makes 1 bond, all right? So each hydrogen makes 1 bond. Now, carbon does make 4 bonds. Notice how it's only making 3 here, so where's the 4th one going to be? Well, the 4th one's going to be right there. Okay, well now this one's making 3, so the 4th one's there. This one's making 3, 4th one's there. And notice here how oxygen is making 2, which it's supposed to be making 2. The only thing we need to do is add the lone pairs, and there it is. So the thing here is that there's multiple central atoms, and the formula tells you what is bonded to each central atom. And that is all there is to Lewis structures. These are actually really fun. I really do enjoy these problems. They're kind of like a puzzle. You got to put them together, make sure they have the appropriate number of bonds. And so make sure that you're really following along this chart here. This chart is really helpful. If you have a situation where there's more bonds or less bonds than what there should be, then you need to verify, as in these, like you had to do in these last 2 examples here. So, all right, so a few elements will have fewer than 8 electrons in their valence level, but they are still stable, all right? So the first one we're talking about is hydrogen. Hydrogen will only have a maximum of 2 valence electrons, right? And that makes sense. It makes 1 bond, there's no lone pairs, and it's in the first energy level, so the first energy level can only hold 2. The next one is beryllium, all right? So beryllium will only have a maximum of 4, and the reason why that is because let's take a look at beryllium. So here it is. Beryllium, if you take a look, can only make it only has 2 single electrons, so we can only make 2 bonds. And when it makes those bonds, each bond has 2 electrons, that's a total of 4. And then boron is the same thing. Boron was okay with a maximum of 6 because if we have boron here, notice how it has 3 single electrons, it will only make 3 bonds, and when it does make those bonds, it'll have a total of 6. Now this next one is really important. And this next one, a lot of people ask, why is it that some noble gases have a certain amount of electronegativity? And this right here is the explanation why some noble gases can actually form bonds. So in elements in periods 3 through 7, so that's rows 3 through 7, are often able to expand their octet. And what that means is they can have more than 8 valence electrons. And they can have up to 5 or 6 pairs of electrons, which if they had 6 pairs, for example, this one has 6 pairs, it is going to have 12 electrons. That's a lot. All right, now this is only possible for elements in the 3rd period through 7th because they have empty d orbitals. If you remember, in the 3rd row, or in the 3rd energy level, that is where we first have d orbitals. There is a such thing as 3d. There is not a such thing as 2d. And so the d orbitals actually allow for the expansion of the octet rule. And the reason why that is because those orbitals provide a location for those electrons to go, for those extra electrons to go. And so when you are building these structures, for example, we're gonna talk about how to do this. The same rules apply. If something is clearly making more bonds than it should, you need to force the bond and count the electrons. All right, so on the bottom here, what we're gonna do is we're going to, I want you to pause the video, all right? I want you to look at your notes, and I want you to answer these, and I want you to circle everything, each compound that is violating the octet rule. And I really want you to do this because there is a big mistake that people always forget, but then when they see it, it's like, oh, that makes sense. So I want you to pause the video, and this is how you know. If it's making more bonds than it should, then it's violating the octet rule. If it's any of these, if it has any of those three elements, it's violating the octet rule. So that's really it. So if it's making more bonds than it should, it's violating the octet rule. Or if it has any of those first three elements, hydrogen, beryllium, or boron, it's violating the octet rule. So go ahead and pause the video and answer that question. All right, I'm going to go through and circle them all. All of those are violating the octet rule, all of them. First off, anything with a hydrogen. Anything with a hydrogen, hydrogen is violating the octet rule. It only has 2 valence electrons. That's probably the biggest thing that people forget. Hydrogen itself violates the octet rule. It's okay with a maximum of 2 electrons. Next, this one is also violating the octet rule because nitrogen typically makes 3 bonds, but it's making, or actually that one's, I'm sorry, I take that back. This one is violating the octet rule because xenon typically only makes, actually it doesn't make any bond because it's a noble gas, but it is somehow making bonds here because, again, it has those empty d orbitals for there to be extra electrons to go. This one here, again, sulfur typically makes 2 bonds. If you take a look, it typically makes 2 bonds. It's similar to oxygen, but it's making 6. And then boron. Boron only makes, is okay having 6 valence electrons. And if you take a look, if you draw the structure, you'll see it only has 6 valence electrons. All right, let's go ahead and do this last problem here where we're going to draw the Lewis structure of something violating the octet rule here. So there's 6 fluorines. All right, so evenly spread them out. Now sulfur typically does only make 2 bonds, but again, because the formula is telling us, what we're going to do is we're going to force it to have bonds. And then what we do is we add the lone pairs on all of these. And so this is where we have a blast writing all these dots. And there's a lot of them. Now, then what we need to do is, because it's violating the octet rule, we then need to, and sulfur does have two lone pairs, we then need to count, all right? So sulfur has 6 valence electrons. Now fluorine has 7, however, there's 6 fluorines. And when you add all of that together, you get 48. And so if you were to count all these electrons though, if you were to add them all up, we have 2, 4, 6, 8, 10, 12, and then we have to count up all the lone pairs. You will get, when you add everything together, you will get 52. And so what that tells you is that there's 4 extra electrons than there should be. And so again, if we have too many electrons, what we do is we remove from the central atom. And that is the structure. So again, you put the bonds around it, you force it to have the bonds, and then you have to count the electrons and remove the appropriate number of electrons from the central atom. So that is going to be it for this video, and I hope you are able to do those practice problems as well, and you have a great day.